One area that I've seen students struggle with in statistics is this notion of, say, expected value of a random variable or the standard deviation of a random variable. And I completely understand. It is one thing to already have a data set. You're looking at the data and you're saying, well, what's the mean of that data? What's the standard deviation for that data collection? Okay, well, that's one thing. But with a probability distribution, in some sense, you are modeling something that it hasn't even happened yet. And so how can you have a mean or a standard deviation of data that isn't even there? You just have a random variable that follows a set of rules. And so we're going to look at that together. What I'm about to show you, I want to be clear. It would work for absolutely any distribution, discrete, continuous. It just so happens that when it comes to coding, it is the easiest to work with the continuous uniform probability distribution because of how the RAND function works in Google Sheets or Excel. What I have is a continuous uniform probability distribution with a lower bound of 0 and an upper bound of 10. And according to what the distribution rules state, the theoretical expected value is right at the midpoint at 5, and the standard deviation is 2.887. We'll take a look at these just very quickly. We find that if every value is just as likely as every other value along a bounded range, then the midpoint is going to be the long run average. And that comes down to symmetry, right? Like some of our values are going to be above, but they're going to perfectly offset with an equally likely value that lives just as far below. And so in a sense, we can think about folding this rectangle on itself. And where would you fold it? Well, you'd fold it right in the middle. Whenever you have a symmetric distribution, say like the bell curve, the mean and the median end up being the same, but symmetry has to hold in order for that rule to work. The standard deviation really comes down to range. If our range is wide, then the range of possibilities, the average distance from the mean goes up. And if the range is low, we're going to find that the standard deviation is also low. And that's exactly what the standard deviation formula is. It's the upper bound minus the lower bound, in other words, the range, divided by the square root of 12. You need some calculus to understand, like, well, why are you divided by the square root of 12? But just to kind of show you this is the case, I'm going to come up with different values that still have a center point or a midpoint of 5. I'm going to go with 4 and 6. Well, the midpoint of 4 and 6 is still 5, but our standard deviation fell quite a bit. It fell from like 2.88 down to 0.577. So we'll go back and work with the original values. I've created a list of like 2,000 values that are randomly selected, and they must all fall in a uniform distribution within the range that we specified. So in this case, our range was 0 to 10. So all of our values fall between 0 and 10. And the question is there anything special about these values? Absolutely not. Every time I just kind of enter in a data point, like say I just put 1, all the values change, right? Notice the change here, 6.97, 710, and they're updating it. Well, let's look and say my theoretical mean and standard deviation was set at 5 and 2.887. So with a list of about 2,000 values, what is the mean of these 2,000 values? Well, it came out to 4.986. And what about the standard deviation of these 2,000 values? 2.843. How's that stack up against the theory, what the theory said that they should be? Well, the theory said that they should be 5 and 2.887. So it looks like our mean for our observed data turned out to be just a little bit below what we believed was going to happen. And the same is true of the standard deviation, just a little bit below what we believed was going to happen, 1.51% below, 0.28% below. And we'll find that every time we make a change, it's going to change. And we're going to be off, right? But we're not going to be off by a lot. And that's the big part. Okay, well, the actual mean turned out to be 0.17% bigger than the sort of predicted mean. And the actual standard deviation turned out to be 0.77% less than the predicted standard deviation. Well, that's really not bad, right? What we're looking at when we're looking here is our single best guesses, called point estimates, as to what the mean and standard deviation of a population, of a large population, that was governed by the uniform probability distribution with boundaries set at 0 and 10. And what we find is when we have lots and lots of these populations, the prediction is not perfect, but it holds up pretty stinking well. Your turn, Lines on Clay users. Build up your intuition by going to the Google Sheet that we've prepared for you. Go to the Continuous Uniform Probability Distribution tab and change up these values and see for yourself how the theoretical expected value and theoretical standard deviation lines up with the reality just by playing around with these numbers here. Just press 1, 1, 1, 1, and see how it changes things up. And it's pretty cool.